Hello guys, welcome to Tom's SAT. Today we are going to hit the simple but broad topic of triangles. And today we are just going to focus on the angles and sides and areas of triangles. And we're going to talk about the basics of how to find missing angles and sides. And then we're going to talk about similar triangles, which is a very common topic in dealing with triangle problems in the SAT, as well as some situations where they get used. And then we'll talk about some special right triangles. And then lastly, we'll finish up on tough problems of the day. So to start, we're going to learn some basics. Okay, so first we're going to talk about the basics of the angles and sides of a triangle. The obvious things that you should already know is that a triangle has 3 angles and 3 sides. And when I try to say 2 angles are congruent, meaning that they have the same measure, I use these rings. And when you have an equal number of rings, that's saying the 2 angles are congruent. Likewise, if I were to put in dashes, that is to imply congruent sides, meaning sides with the same length. So in this triangle here, I am demonstrating to you that I have 3 different sized angles as well as 3 different lengthed sides. And first thing I want to teach you guys today is probably one of the simple rules you already remember from school, which is that in any triangle, the interior angle sum is always going to equal 180. So in a triangle, I have 3 interior angles. And if I were to take the measure of each one of those angles and add it up together in an equation, by rule, it is always going to be giving me 180 degrees, which means that anytime you have 2 angles in a triangle, the third angle is right around the corner. Okay, next thing we're going to learn is the concept of linear pairs forming supplementary angles. So in this case, I have an exterior angle over here to this triangle where the exterior angle is angle ACD. And you'll notice that angle ACD is adjacent to angle ACB, and it's on a straight line together. So this relationship right here is what we would call a linear pair. And if you remember that any straight angle is always going to be 180 degrees, then you'll know that the green angle and the purple angle here, they're going to add up to 180 degrees. And furthermore, not only do you know that, there is a relationship that you can describe when you have 2 angles that add up to 180, and that word is supplementary. And that's one thing I want you to learn. If 2 angles make a linear pair, they're supplementary. Another rule that you're not going to see nearly as much, but it's good to have in the back pocket, is that whenever you take 2 remote interior angles, which are 2 angles inside the triangle that are not adjacent to the exterior angle, the 2 remote interior angles always adds up to the exterior angle. So in this case, down here, I showed you that angle ACD plus measure of angle BCA has to equal 180. Another rule you should learn is that angle B plus angle A is going to give you angle ACD. And that's 2 rules you should learn about the exterior angle of a triangle. And then we move on. Okay, so this right here, you'll notice that angle ABD and angle DBC are inside of a right angle. So you can probably guess that the measure of those 2 angles added together is going to equal 90. And when you have that relationship, the angle pair is called complementary. And the next relationship we're going to see is over here. Um, and this doesn't necessarily have to do with a triangle, but you'll see it often enough that it's good to know. So when you have two lines that intersect each other at one point, four angles get made. And whenever this happens, the angles that are opposite of each other are always going to be congruent. So in this case, that angle on the bottom is 34 degrees. So then the opposite angle with a question mark is also going to be 34 degrees. And if you combine this knowledge with the fact that linear pairs are supplementary, that means the angle next to the 34 degrees here has to be 146 degrees. And using that vertical angle rule again, the opposite angle is 146 degrees. So vertical angles is a very powerful tool for you to use because it always leads to things being congruent, so it lets you find numbers rather quickly. So this talks about the angles, the basics of angles in a triangle. And now we're going to work on the differences in sides of triangles. So in terms of sides, there are three main ways to break down types of triangles that you're dealing with. There are triangles where you have 0 congruent sides, meaning that you have a triangle with 3 different side lengths. There's triangles with 2 congruent sides. So if I want to mark up 2 sides that are congruent, I'm going to put a single dash on 2 sides. And then there are triangles where all 3 sides are congruent. So then I would mark up 3 sides with a single dash to show you that all 3 are congruent. And each one of these classifications has a name based on the number of congruent sides it has. 0 congruent sides, it's called a scalene. 2 congruent sides is called isosceles. And 3 congruent sides is called a equilateral triangle. And each one of these triangles have a special thing that I would like to teach you right now. For right now, it's good just to remember the different classifications. But now I'm going to show you a couple implications that comes with knowing these things. So in a scalene triangle, what I'm about to show you is true for all triangles, but I think it's the easiest to demonstrate with the scalene, which is that when you have any polygon, the smallest angle in the triangle always corresponds to the smallest side. So this is angle A right over here. And when I say corresponding, I'm talking about the side that's opposite of it. AC and AB are adjacent sides to angle A, but side CB is the corresponding side. And in any shape whatsoever, smallest angle always corresponds to the smallest side. And that logic also applies to the largest angle and largest side and the medium angle and medium side. So just like the smallest angle leading to the smallest side, the largest angle is always corresponding to the largest side. So if I take angle C right here, the corresponding side is AB. So then angle C is the largest angle leading to the largest side of AB. And then, of course, logically, it would only make sense that the medium angle leads to the medium length side within the triangle. And that is a good thing to remember when you're dealing with triangles if you just need to estimate the order of sizes in terms of angles or sides. Next thing I want to show you is about isosceles triangles. And what you're learning is that when you have matching corresponding sides, when you have corresponding sides that are congruent, their corresponding angles must also be congruent. So the side over here on the right corresponds to this angle down here. And the side on the left over here corresponds to this angle down here. And the rule you're learning is if these two sides are congruent, then their corresponding angles are also going to be congruent. And what that does is it gives us ability to find missing sides. So if I know that this angle on top is 50 degrees, and down here I need to find these two angles. I can put y over here so that this is one variable, and then on the angle on the right I can also put a y because the two angles are congruent. And now I can hook up an equation to solve for one of the missing angles. And that's something you get to do with isosceles triangles. As long as you know one angle, you have the ability to find the other two angles because you can hook up an equation with only one variable to solve for. And now we're going to talk about that equilateral triangle. So just like isosceles triangles, corresponding congruent sides lead to congruent corresponding angles. Same thing over here, 3 congruent sides means I have 3 congruent angles occurring. And the nice part of this is if you remember that all 3 angles are congruent, then I can set up a variable for each angle. And the variable is the same throughout, so that when I put it together into an equation, x plus x is 3x, which is equal to 180 degrees altogether, so that x should be equal to 60 degrees. And the thing to remember here is that this isn't something you need to prove to yourself. This is something that's just universally true. Whenever you're dealing with an equilateral triangle, you automatically know that every single one of these angles is going to be 60 degrees, and every one of these 3 sides is going to be congruent. That's a good rule to remember for equilateral. So the thing to remember is right now is that congruent sides lead to congruent angles, and also congruent angles lead to congruent corresponding sides. And that's the different kind of types of triangles that we can deal with. And now let's move on to another set of basics. And this time we're going to talk about right triangles and area. So let's talk about right triangles first. This triangle I'm presenting you with is a right triangle, and you know that because one of the angles is the right angle, given by this little box thing over here. That implies that this is 90 degrees every time. And first thing we're going to talk about is the concept of hypotenuse. A hypotenuse is the longest side of a right triangle, and it is always going to be opposite of the right angle or corresponding to the right angle. It's interchangeable which word you decide to use. And a good way for you to remember which one is the hypotenuse is that the right angle is always pointing at it. So that's a good way for you to remember which one the hypotenuse is going to be. And the other 2 sides of a right triangle that's not the hypotenuse, those sides are called legs. And now that you know the anatomy of a right triangle, we're going to teach you one really basic, famous theorem that you're going to be using quite a bit in the SATs, which is the Pythagorean theorem. Pythagorean theorem states that if you have a right triangle, and let C represent the hypotenuse, and you let A and B represent the 2 legs, doesn't matter which one's which, then you get to write an equation that's always going to be true, which is A squared plus B squared is equal to C squared. And the reason why this theorem is so powerful is because with this formula, as long as you know 2 sides of a right triangle, you can always algebraically figure out what the 3rd side is going to be, as long as you know how to solve a basic equation. And that's a very convenient way for us to find, or a very effective way for us to find missing 3rd sides in right triangles. However, as you can probably guess, with all those squares, you're going to have to do quite a bit of calculating every time you use a Pythagorean theorem, because there's no multiple numbers to square and then subtract the square root in order to get to your final answer. So I'm going to show you something else that's very important. While the Pythagorean theorem will always work, very often you're going to be dealing with decimals, but there is such a thing called a Pythagorean triple. And what Pythagorean triples are, they are triplets of numbers that fit the Pythagorean theorem perfectly. Triplets of whole numbers that fit the Pythagorean theorem perfectly. So an example of a Pythagorean theorem is 3, 4, 5. And the reason that's a Pythagorean triple is because if I put it into the Pythagorean theorem, where remember the last number is always the C value. If I put it through the Pythagorean theorem, I get 3 squared plus 4 squared is equal to 5 squared, which when we check that math, it checks out. Now we know, and now what we get to do is if I have a right triangle and I have two sides of that triangle and it happens to fit a Pythagorean triple, I can really, really easily get to the third side if I just memorize what the Pythagorean triple are. And that's a really, really nice tool to have. Now, you'll notice that you'll probably make the guess that there is an infinite number of Pythagorean triples out there. And all I did just now was show you one of the fundamental ones. But knowing one of the fundamental ones actually does a lot for you, because not only does 3, 4, 5 work, but every multiple of 3, 4, 5 also works. So for example, if I did 6, 8, and 10, just multiply everything here by 2. 6 squared plus 8 squared equals 10 squared. That still checks out as a Pythagorean triple. And what this is really showing us here is that if you have a fundamental Pythagorean triple that works, that means every multiple of that Pythagorean triple also works. So if I were to deal with a right triangle where my sides are 600 and 800 for my legs, then it's really not too hard for me to figure out that the hypotenuse there has to be 1000. And recognizing this saves you a lot of time when you're working through a problem and trying to figure out a third missing side, especially when the numbers are easy. And 3, 4, 5 isn't the only fundamental Pythagorean triple. There are other ones to remember. There are other ones that you can memorize and use. For example, another one would be the 5, 12, 13, where you get 5 squared plus 12 squared equals 13 squared. And that also checks. But I will tell you from experience and from understanding how the SAT works that the 3, 4, 5 rule is something you're going to want to remember, and you're going to want to be able to use it extensively for multiples of that Pythagorean triple. And with that knowledge, we're going to move on to talking about areas. There are two area formulas that you should know. One you learned from middle school, one you're going to learn right now. The one from the middle school is area equals 1/2 BH, where the B stands for the base and the H stands for the height of the shape. Now, the length of the base is always something you actually decide, but for convenience sake, you're always going to decide the side that's easiest to look at as the base. So the base, you just pick a side on. So that will be my B in this case. And the height is represented by the perpendicular distance between the highest point on the triangle and the base of the triangle. So if this is the base, then the highest point is this green point up over here. And remember, I didn't just say distance, I said perpendicular distance, meaning that when I draw that segment in for the height, I got to make sure it makes a 90-degree angle with a base. And this right here would be the height. And once you get both these numbers, you can just do 1/2 times B times H and get your area. Remember to use units squared, because we're talking about two-dimensional space here. When we talk about area, we're talking about how much area something covers up. So then you have to do whatever units you're using squared. And that's the one you've already known. However, the SAT is not nice enough to always be giving you the base and the height of a triangle for you to find the area so easily. There are going to be times where they will, instead of giving you the base and the height, they'll give you an angle, and then the lengths of two sides that are adjacent to that angle. So notice that in this example, I have angle A as 40 degrees right here, and even though I have the base of 7, they didn't give me any height for this triangle. So I would have to find that height in order to use this formula. But alternatively, anytime you have this configuration where you have an angle stuck between two sides and you know all three numbers, you can plug it through the alternate area formula of 1/2 sine of A times B times C, where the A would have to be the angle, and the B and the C would have to be the side lengths. So that if I were to put this problem into the area formula of a triangle, it would be A is equal to 1/2 times sine of 40 degrees times 7 times 6. And notice that we're using capital letters. When we use these formulas, capital letters represent angles and lowercase letters represent side lengths. And now that I have all this, I can actually just plug this into the calculator so that I can get my area directly without having to find the height. Now, real quick, when you're using the calculator to do math with angles, make sure you're doing everything in degrees unless you're specifically meaning to do it in radians. So make sure you get it into degrees before you move on. And now we can go. We are doing 1/2 times sine of 40 degrees times 7 times 6. And with that, I get 13.5. So then my area for this question, or for this triangle, will be 13.5 units squared. And that's an alternate formula to use that comes in handy a good chunk of time. And now let's try some example problems for the basic triangle stuff here. Question A. No calculator. I got a triangle with angles A, B, and C, and the triangle above, A is equal to 34. What is the value of B and C? So this one right here is 34, and I can set up an equation for this situation right now. And I know normally I wouldn't be able to solve for B or C because this is one equation with two variables, so that's impossible to solve that way. But if we realize that they're just asking for what B plus C is equal to, then I can just minus 34 on both sides of the equation. And then B plus C would then have to be 146. And that's how you do that one. And now let's try something a little more complex and requires a little more creativity. Okay, so for this problem over here, we need to get measure of angle RVS here, or just this angle, which is going to be X. So that's going to take some effort, but we'll get there slowly but surely. First thing they tell us is that RT is equal to TU. And that actually gives us some information right off the bat, because that tells us that these two sides are congruent, which means that these two angles, angle R and angle U here, must also be congruent. So real quick, I can figure out those two angles right there to say that both these angles are 33 degrees. And now for this small triangle down here, if I can figure out the angle on top, I can use the interior angle sum to get angle RVS right here. So I'm going to have to find some other ways to get that second angle. So what I may notice is that STR makes a linear pair with RTU. So if this is 114, this one's got to be 66 degrees right over here. And if this one's 66 degrees right here, and let's name this thing Z or something, then 31 plus 66 plus the Z must be equal to 180. And then Z becomes equal to 83. And in this case, if this is 83 right here, then the bottom one here must also be 83. And now that we know that one's 83, we can wrap the problem up with 83 plus 33 plus X is equal to 180. And in this case, you can pretty quickly get to that X is equal to 64. Now, I know some of you guys solve this equation on the regular, but I want you to notice something that's just a tiny bit lazier than usual. If you we know that in this equation, I'm going to have to add these two pieces and then subtract on both sides. And when I combine these two, I might not know what's going to be in the hundreds place or ones place or in the tens place, but I do know that the last digit is going to be a 6. And I'm going to be subtracting by that. Whatever I subtract by, I know that the ones place is going to be a 6. So then when I solve this equation for x, I don't know what's going to be in the tens place, but the ones place is going to be a 4. And the reason why I'm doing it in such a shoddy way, where I don't even think about the tens place value, is that all 4 answer choices have different ones place numbers. And just knowing that there's only one option with a 4 in the ones place means that I don't actually need to know what the tens place number is to solve this quickly. And that's a very methodical and straightforward way of doing this problem. Now, this method absolutely works, but remember during the beginning of the lesson, I said that it's important that you guys are looking for shortcuts. So I'm going to show you an alternate way to do this problem, starting from a certain step. Okay, so we're going to get to this step right here. Remember early on that we figured out both these angles out here are 33 degrees. Now, if I know that both those angles are 33 degrees, a different triangle I can pick up is this triangle right here, where you notice that I already have angle S and angle U. So then angle SVU shouldn't be too hard to find. These two add up to 64. So then this one right here has got to be 116 degrees. And if this is 116 degrees right here, then the supplementary angle must then just simply be 64 degrees. And notice that when I do it that way, I didn't have to do this math, I didn't have to do this math, I didn't have to do this math. And the more steps you get to minimize with facts you know, the less likely you are to make a mistake. And also, it's just less brain power you have to use, and you don't have to spend as much time on it. And if you guys remember a really obscure rule, you may notice that once you talk about this triangle, angle RVS, or the X that I'm looking for, is an exterior angle. So the two remote interior angles, which are the two angles that are not adjacent to the exterior angle, if I add up these two together, I get 64 degrees, and that's a rule that always works, so I could have also gotten the answer that way. So I just showed you 3 separate ways to really technically get the answer with a sure thing. And that's a lot of what you guys are working on, is trying to see if you can find the shortcut before going about it the really long way. And with that knowledge, we move and we talk about similar triangles. So similar triangles is a relationship describing 2 different triangles, where this pretty much shows you an example of it, and I'll break down the rules right now. The squiggly symbol here basically refers to is similar to. So I am saying triangle ABC is similar to triangle DEF. And 2 rules happen when you say 2 triangles are similar. First of all corresponding angles are congruent. So when I say corresponding angles, I'm saying B matches with E, A matches with D, and C matches with F. And if you know that 2 triangles are similar, then all those matching angles are going to be congruent. And likewise, if you know that all these matching angles are congruent, then the 2 triangles must be then be similar. And that's a really easy rule to recognize and prove. And now we'll try to show you the other thing here. So another thing you learn about similar triangles is that not only are all corresponding angles congruent, all corresponding sides are proportional. And if you forget what proportional means, proportional basically means you have multiple ratios, be it 2 or 3 or 4. You have ratios that equal the same value. And one way we can check this out is by recognizing that if you look at the sides of 2, 3, and 5 over here, and the sides of 4, 6, and 10 right here, all the matching sides between AB and DE and AC and DF, they're all multiples of each other, as in everything over here is always twice the size of this one. So that's figuring out proportional sides by scale factor, which is if you know everything's just multiplying by 2, then they're going to be proportional. But another way to do it is to do it based on making the fractions equal each other, and that's really the true definition of proportion. It's a equation of ratios. And what we can do is match the corresponding sides and see if we get the same fraction every single time. So before we put all 6 numbers in, I like to keep my information organized so it's easier to think about. So what I like to do is set up an extra fraction on the side here where I label which is a small triangle, which is a large triangle. And then on vertically, I label them as ratio 1, ratio 2, ratio 3, because I'm trying to remember that these vertically, they're supposed to match. They're supposed to be matching sides between the 2 triangles, and horizontally, the sides all belong to the same triangle. So for example, if I stick 2 on top, that's 2 of the smaller triangle, and the matching side would be the 4, which is segment ED for the large triangle. If I stick a 5 on top, the bottom is supposed to be a 10. If I stick the 3 on top, I know the bottom is supposed to be a 6. And setting it up like this makes it easier to pull the numbers. And now we can check they're proportional by simplifying them all. And in this case, all 3 pairs of corresponding sides give me the same fraction, which basically tells me that all 3 pairs of sides are proportional. And just like knowing if you have similar triangles that your corresponding sides are proportional, knowing all corresponding sides are proportional also tells you that you got yourself 2 similar triangles. So it's a lot like the corresponding angles being congruent. One last thing you should understand about corresponding is that not only do you don't always have to just match it by the shape, but if they give you a similarity statement or a congruent statement, it would always be written out so that the letters, the order of the letters are already corresponding. So for example, if I do angle A is the first letter, the corresponding angle is angle D, which is also going to be the first letter. If I say BC is proportional to EF, you can tell that BC is the second and third letter, just like EF is the second and third letters of their own triangle. So then those sides are also corresponding. So if they give you a similarity or congruent statement, the corresponding points are already made for you. And when it comes to using similarity, I will tell you that setting up good proportions is really your bread and butter for finding missing sides. And with that knowledge, we're gonna try a problem. Okay, so triangle ABC and DEF are shown above. Which of the following is equal to the ratio BC over AB? So situation like this, they haven't actually told us that I have some similar triangles yet. I'm gonna have to see if I can find some similar triangles. But in each right triangle, they already gave me 2 angles. The third one we can find relatively easily because I know everything adds up to 180. And now that I see that in each triangle, all 3 angles are congruent, these 2 triangles are similar. And now I know that for the triangle triangle ABC, they're giving me BC over AB, and I have to figure out what that means in terms of triangle DEF. Now, if I just try to work off each answer choice here, this might be actually a bigger pain in the butt because it's like 4 letters per answer that I have to like mark up and match to see if they fit the situation. So a big part of doing SAT math, especially within triangles and geometry, is you want to be able to make sure you represent information to yourself as easily as possible. So instead of dealing with these 2 triangles being similar and having to like match which sides go where, what I'm going to do is I'm going to redraw one of these triangles so that the problem looks easier to me. I'm going to redraw DEF so that the 32 degrees is down over here, 58's up over here, and just by matching the points of the angles, I know this is F, this is E, and this right here is going to be D. So I can forget about my old triangle, and now they line up, so it's a lot easier to see what I need to see. I need to figure out what ratio is equal to BC over AB. So BC is this one. So then the matching side for the other triangle is DF. So that's going to go on top. And AB is the side on the bottom, and that's the hypotenuse. So then for me, for this triangle, that's ED. And with that, it's much easier to see that B is the answer. And all we did was just re-represent a triangle so that it was nicer to look at for our faces. And that's also a skill you absolutely want to practice when you're dealing with triangles. And now let's move on to the next concept. So there are times when you can prove triangles are similar with angles and sides, but there are also times where you should recognize when you're dealing with similar triangles. And before I show you the triangles, I'm going to teach you a rule real quick. Right now, on the top pair of lines right here, I have parallel lines, and if I were to send a straight line through these two parallel lines, I am making what's called a transversal. It's cutting through the two parallel lines. And what you may notice is that I've just made 4 angles on top and 4 angles on the bottom. And half the angles are big and half the angles are small. And a lot of them look the same. And that's because they are. When you take a transversal and cut it through parallel lines, you are creating essentially 2 quads of congruent angles. So all the small angles here are congruent because they're vertical, and these 2 are congruent because they're vertical, and these 2 angles and these 2 angles end up being congruent. And then likewise for all the obtuse angles here, same thing applies. All the large angles become congruent. And in school, you learn the theorems for this, like corresponding angles, alternate interior, alternate exterior, and same side interior angles. But when I'm just going to show it to you in terms of position, you're essentially creating 2 sets of congruent angles. And not only do you know that, the small angle plus the large angle is always going to be supplementary. So it's always going to sum to 180 degrees, which is also something useful to know. And knowing that this is the case, I'm going to show you 2 situations where you should recognize similar triangles almost immediately. So we're going to try the problem on the left. Not a problem, but a setup here. I have 2 parallel lines already. That's nice and easy to see. And what I'm going to do is I'm going to draw one line through this way, so that's one transversal, and then I'm going to draw a different line this way, and that's my other transversal. And what happens now is I have 2 sets of triangles being made. Now let's mark some congruences up. These 2 are congruent because they're vertical angles. And now if I look at this blue line as my transversal 1, this line is cutting through these 2 parallel lines so that this angle, this small angle, and this small angle end up being congruent. So now I have 2 pairs of congruent angles. And if I think of this purple line as a transversal 2, then I know that this small angle and this small angle is supposed to be congruent. And now that we know that these 2 triangles have 3 sets of corresponding congruent angles, then we know that these 2 triangles are similar. And that's rule number 1, situation number 1 for when you make similar triangles is when it's in between parallel lines. And with that knowledge, we can suddenly start setting up proportions and do a lot more math. Another situation where you're going to deal with similar triangles is called a side splitter, which is when you have a triangle and you draw a segment or line through the triangle that is parallel to the base of the triangle. So what's happening right now is I drew this red parallel line to the base, and I just made myself two triangles. I made myself the small triangle on top, and then I still have my super large triangle that was like my original triangle. And I'm going to show you how they're similar. So both triangles share one angle up over here, so then it would only make sense that those two are congruent. If I look at the left side of this triangle as a transversal, then these two angles are corresponding angles, and then they must be congruent. And then on the right, if I look at the right side of this triangle as a separate transversal, then these two acute angles here are also corresponding angles that must be congruent. And with that knowledge, we now immediately know that I have two similar triangles right over here. And just keep in mind that if this is a 3 and this is a 5, this left side of the small triangle may be a 3, but the left side of the bigger triangle is the sum of those two pieces, so then that would be an 8. And I'm drawing these two triangles out because you're going to see this information plenty of times, and it really may be useful for you to redraw the triangles so that it's easy to see the things that you need to see. And with that, this is called the side splitter. That's another special situation where you should recognize similar triangles almost immediately. And now we move. And here we are with our first problem. Before I even read this question, I'm almost positive I'm going to have to deal with some similar triangles because I have two parallel lines right here. And I have a triangle right here, and two parallel lines are going through it. So I know that each of these right triangles is going to be similar. And now let's see what information they are giving us. So triangle ADG has an area of 6 square units. And what I'm actually going to do is I'm going to move the stuff out here. And what that does for me is it helps me organize my information. So area is equal to 6. And they're telling me that AD must be equal to 3. And for the other right triangle here, so AEF, the hypotenuse is also going to be 3. And I know that for this question, their job is to, my job is to find FE over here. So at this point, most of the problem is already represented. We just now need to find, we now need to be able to get a pair of corresponding sides between these two similar triangles. We already know they're going to be similar, we just got to figure out how to set it up. So if I have X over here, that means I'm going to need to find the corresponding side over here. And let's do that first. So they already told me that the area of triangle ADG is equal to 6. So if I do area is equal to 1/2 base times height, and we get rid of the middleman here and make the formula equal the area, I have 1/2 times 3 times h equals 6. When I solve this, I get h is equal to 4. And now I know h is equal to 4. And now if I try to put numbers into this proportion, I want to make sure everything's nice and organized. So I'll do the small triangle on top, large triangle on the bottom. And I'll put ratio 1 over here, ratio 2 over here. So vertically the sides need to match. Horizontally the sides need to belong to the same triangle. So for the small triangle, I can put X up on top over here, and then the matching corresponding side would be 4 for the large triangle. And now you might notice something. For the small triangle, if I put a 3 up over here, you'll notice that the 3 I have on the bottom is not the corresponding side, so that wouldn't be the number that I would actually use. For you to put numbers into a proportion, the sides need to be corresponding. So my job now is actually just to find the hypotenuse, which if you're quick and you remember the previous lesson, one of my legs is 3, one of my legs is 4. So then that's a classic Pythagorean triple where the hypotenuse is going to be 5. And you can use Pythagorean theorem to do that, but I personally think that takes way too long. If you remember your triple, it's easy to derive these numbers real quick. And now, if I put 3 on top, I know I'm going to put the 5 on the bottom. And now I can cross multiply. 12 equals 5x. X equals 12 over 5, which is what I get for A. So situations like these, if you re-represent the information and write down what you know, you can methodically get to the answer without having to worry about whether you made a mistake somewhere. And we move. All right, now that we're done talking about similar triangles, we're going to talk about the concept of special triangles, special right triangles. And the two types are 45, 45, 90 and 30, 60, 90. As you can probably guess, they're referring to the angles of the right triangle. And the reason we call them special is because with these two right triangles, as long as you know one side of the right triangle, you actually have the ability to find every other missing side of the right triangle. And I'll show you what that means as a rule. So let's talk about the 45, 45, 90 first. First of all, recognize that if these two angles are congruent, that means their corresponding sides must also be congruent. And if I say this bottom side here, length is side S, where length is S, that means this side length over here, you guessed it, would also be S. And that's nice. That's nice knowing that whatever one side is, the other side's going to be the same thing. Now, the harder rule to remember for 45, 45, 90 is that the hypotenuse, if the leg length is S, the hypotenuse is always going to be S times radical 2. As in whatever the side length is for one of the legs, the hypotenuse, you would just get it by multiplying by the S by radical 2. And what that does for us is it gives us very clear ways to get from one side to another. If I already know what S is equal to, all I need to do to get to the hypotenuse is to multiply by radical 2. And if I already know what the hypotenuse is, all I need to do to get to one of the legs is to take that number, whatever that number is, and then divide by radical 2. And that's going to give me the side length right here. And obviously what works for one side here will also work for the other congruent side. And that's one of your special right triangle ratios. The other special right triangle to be aware of is the 30, 60, 90, which also has a specific set of ratios, except this time it's a scalene triangle, so we're going to have 3 different formulas for the 3 different sides. So the easiest one to remember is that the side that's opposite the 30 degrees, think of that one as side S. So that's the one we're going to that's the number that's going to be the smallest side length in this triangle right over here. And the formula for the length of the hypotenuse is always going to be 2s. So if I know the side that's opposite the 30 degrees, I would just need to multiply it by 2 to get to the hypotenuse. Let me write it down here actually. And with that, the side that's opposite the 60 degree angle, corresponding to the 60 degree angle, is just radical 3s. So whatever s is, if I want to figure out the side length opposite the 60 degrees, I just multiply by radical 3. And with that knowledge, we can also do the backwards version of this. So if I know the hypotenuse and I want to get to the side length, I just need to divide it by 2. And if I know the hypotenuse and I want to get from the hypotenuse to the 60 degree side, I would divide by 2 first to get to s, and then multiply by radical 3 to get to radical 3s. And likewise, if I have radical 3s and I want to find the other 2 sides, I would first get to s by dividing by radical 3, and then multiplying by 2 to get to 2s. And these ratios are always consistent, meaning anytime, as long as you remember the formulas well and you know how to work it, anytime you know one side of one of these, you know the rest of them. And we move. So this is an example of a 30, 60, 90 triangle problem right here. I just made this one up. Knowing that the side opposite the 60-degree angle is 18, I'm going to find side x and side y. Now, the way I like to approach these isn't to actually find it based on the variables they give me. I actually like to do it based on writing the formulas out to begin with. Because what that lets you do is it lets you very quickly figure out what variable you're trying to isolate and use to get to the number you need. So 18 equals radical 3s. If I want to get to s, I'm going to have to divide both sides by radical 3. In which case, when I do 18 divided by radical 3, I get 10.4. And now that I know s is equal to 10.4, then the 2s must be 20.8. And now I get to go back and say, okay, so then x is equal to 10.4 and y is equal to 20.8. And that's a really effective way to use your formulas to do 30, 60, 90s really quickly. And now we move. Okay, so now we're going to use that knowledge to do the converse of what I just showed you. So this problem right here, I know that AB is parallel to BC, or AD is parallel to BC, and they are telling me that CD is equal to 1/2 of AB. Now, there is a way to mark it so that you can say S is AB, and then CD is going to be 1/2 of S. But overall, that's not a way I like to do it because I think fractions are gross. You should avoid them when you can. This just means that CD is twice the length of AB. So what you can do is make S equal to CD and then make AB 2S. That's just a little bit easier to think about because once you find S, you don't have to deal with fractions. You just multiply by multiples. And my job is to find angle B, which is this entire angle over here. So we're going to have to use some technique here. So first of all, the thing you might notice is that you can take this trapezoid and break it down into a rectangle and a triangle. So I can cut this into a rectangle right here, into a right angle. So then this one right here has to be a 90-degree angle, which means D is already a stupid answer because my angle is obviously going to be bigger than 90. So now it's really just a matter of getting this angle out here. And I'm going to mark this point E so I can call this angle ABE. And what you might be able to use now is that if this is a rectangle and CD is S, that means BE is also S. And now you might be noticing that I have the ratios of a 30, 60, 90, meaning that the 30-degree angle must be where A is. Oh, yep, because that's the one that's opposite of S. And likewise, if that's the 30 and this is the 90 opposite the 2S, then the 60-degree angle has to be right over here. And without even remembering that the formula is radical 3s, because I don't really need it, I can now solve this problem by saying it's got to be 60 plus 90, which is going to be 150. And that's how we can work through that problem relatively quickly. And now let's wrap up on our tough problems of the day. So the problems that we're going to do today are pretty technically approachable if you just take the time to do it. But I want to show you the importance of looking for a shortcut as well as representing your information so that's easy as possible for you to read. First things first, I have this triangle over here. My job is to get to the length of AD based on what seems to be two 30, 60, 90 triangles that they've given me. And first of all, I know that the hypotenuse here is 12, so this is equal to 2s, which means that s is equal to 6. And then BD over here, this is going to be equal to 6 radical 3. And now what I know is that the 6 radical 3 is opposite the 60-degree angle, so this is going to be radical 3s. And if I want to get to the side that's opposite 30 degrees, this is s, so I just need to divide both sides by radical 3, in which case I get to s being equal to 6, and then I'm done, nice and easy. However, you'll notice that I had to use those rules like 3-4 times just now, and when you take that many steps, you're liable to make mistakes, plus it took me a bunch of time. However, if we go back to just this step right now, you may notice that these two angles on the left and right are 60, and the 30 plus 30 over here means that this angle must also be 60. So what I'm really dealing with in this situation is an equilateral triangle. And we knew that this side was 12, and they are pretty clearly just asking for half of the base. So then it shouldn't be too hard for us to figure out that if the whole side is going to be 12, then half the base is going to be 6. And now we have that problem done within the span of 10 seconds instead of like 45 seconds. And that shortcut might just feel like it saves you time, but it also saves you brain energy and the time it takes to represent work and to use higher level thinking math. By equating this to like such an old school topic of an equilateral triangle, we cranked out that answer in like 10 seconds. And that's going to be something that you want to see. Think with triangles, think about whether you can re-represent things in your head to make it easier. Last tough problem of the day. I chose one of these problems that look like a paragraph, so so you can take down the important information and represent it so it's easy to look at. Read the question first. They want us to find x. Right off the bat, I should kind of have a guess that I'm going to be dealing with similar triangles because I have these two sides that look like parallel lines. And furthermore, notice that I have these two angles congruent, these two angles that are attached to a transversal being congruent. And what that tells me is that means the two lines that the transversal is cutting through, must also be parallel. So this is going to be a problem where I'm going to have to deal with two similar triangles. So we're going to get that proportion ready. And and we need to find x, and they're giving me some side lengths, so the fact that we're talking about a summer camp counselor hardly matters at all. And now they give us the 4 side lengths, respectively. AB is 1800. Let's see, EB is 1400. BD is 700, and DC is 800. Okay, now that all the players are in place, I'm going to do just a little bit more labeling. If we already know these two triangles are similar, those two angles are congruent, these two angles are vertical angles, so then lastly, angle A and angle C are the last pair of congruent angles. You may not feel like that's important, but it's always good to have as much information down as possible. It just makes the problem easier. And now, when I put this into the proportion, I'm not ready to put everything in just yet. I'm going to label everything. Let's do small triangle over a large triangle, and then ratio 1, ratio 2. And for the small triangle, so I can start filling this from anywhere and make it easy. So large triangle, I'm trying to find x. So then the corresponding side for that side is the 800. And for the ratio on the right, I know I'm going to need to use the 700 for the small triangle because that's the only other number there. And when I try to choose between 1800 and 1400, I can make that decision based on the segment they're giving me. So the segment they're giving me is BD, which is between the single ring and the 2 rings. So then in the other corresponding triangle, the corresponding side is also between the single ring and the double ring. So that's going to be EB, which means the number I'm going to use is 1400. And at this point, we can cross multiply and solve. But pro tip, if you see that your ratio here makes an easy ratio, like it simplifies into 1 to 2 or something silly and easy like that, You can simply think of what x would have to be to fulfill the same ratio. In this case, x has to be 1600 so that I don't even have to cross multiply. And guys, I know for this way of showing you, I organized it so that horizontally it has to belong to the same shape and vertically they need to match, but this is only the way I like to do it, and it's also the way I plan on doing it. It is technically also possible to do it the other way, where each ratio has sides from the same triangle, and you need them to correspond horizontally. So if I try to do it like this, I'm trying to find x over here. I'm going to put 800 over here. And for the small triangle, I know the other side I have is 700. The corresponding side is 1400. And if I decide to solve this equation, x is also going to come out as 1600. So it's not that you have to set it up like this chart every single time, but the thing I'm trying to show you with this whole lesson really is that you want to make sure you have all the basic knowledge down so you can use a variety of applications to go through these different problems. And the key isn't exactly how you set this up. The key is making sure you stay organized with all your information, because with triangles being such a simple topic, they're going to just try to throw you off with different kinds of shapes and different kinds of representations. And you want to make sure you get really, really good at reorganizing the information so that it looks as easily as possible to you. And that is it for today. Hope you guys learned some stuff about triangles.